Welcome back. In the last lecture, I concluded my discussion on stochastic processes and also the modeling of stock prices based on Brownian motion. We start with a very brief recap of what we did up to now, and then we move on to option pricing. That is the agenda for today. We will discuss initially the binomial model of option pricing and then continue and work in a continuous environment framework where we have the celebrated Black-Scholes model. So, let us start with a quick recap. Now, while introducing Brownian motion, I emphasize the fact that just as deterministic curves are an assortment, a combination of infinitesimal straight lines, similarly stochastic curves or curves representing random processes, stochastic processes can be considered as increments of Brownian motion, infinitesimal Brownian motions. There is some sort of a parallelity between the conventional Newtonian differentiation, where we look at the curve, the nature of the curve as an assortment of infinitesimal straight lines, very small straight lines at the very magnified level. And similarly, Brownian the stochastic curves or stochastic processes can be represented by infinitesimal increments of Brownian motion. This is an interesting comparison between the deterministic scenario and the stochastic scenario. If dx is a deterministic increment, then obviously because it has no randomness attached to it, the mean of dx is also dx, and usually, as I mentioned just now, we ignore higher orders of dx while doing Newtonian differentiation. So, the expected value of dx square is approximated as 0, and we truncate the Taylor series at the first order term. The variance in both cases is 0. Why? Because there is no randomness attached in the case of deterministic curves. However, we look at the scenario now in the case of Brownian motion. Brownian motion increments, infinitesimal increments of Brownian motion. The mean of Brownian motion is 0. Brownian motion increment is 0. The expectation value of the square of Brownian motion is not 0. Now, here lies this is perhaps the most important point of distinction between the two types of curves. E of dx square is ignored. It is assumed that it is small enough to be of insignificance, whereas E of t w square cannot be ignored because it is of first order in t. E of t w square is equal to dt, and it is approximately non-stochastic. So, not only is this E of dw square of the first order in dt, and it is also almost non-stochastic because the variance of this expression, as you can see here, turns out to be of the higher order in dt, which we ignore. Variance of dt is variance of dw is dt, just like on the basis of this particular expression, because E dw is 0, E dw square is dt. So, variance of dw is equal to dt. I reiterate, dx square in Newtonian differentiation is ignored because it is the dx function dx increment is assumed to be so small that higher orders are considered insignificant, whereas in the case of dw, the increment of Brownian motion, howsoever small it may be, dw square cannot be ignored because it is of the first order in dt, it is approximately non-stochastic, and therefore, it has to be retained while doing differentiation. As far as the stock price model is concerned, this is the model that we talked about at the infinitesimal level. At the infinitesimal level, we have dst is equal to mu s dt plus sigma s dw, where dw can also be written as z under root dt, where z is what? Z is the standard normal variate. This process, this infinitesimal process, gives us the following Fokker-Planck equation, which is equal, and this is actually can be written in the form of a Langevin equation in this here, where eta t is now Gaussian delta correlated white noise, and this gives us the Fokker-Planck equation, which is given by this, and this has the log normal solution. So, the probability density of the stock price at finite intervals is given by the log normal distribution, as we have emphasized. Now, it is interesting to compare the domains of applicability of the two models, that is the infinitesimal model and the log normal model. Infinitesimal model, I am referring to d s is equal to mu s dt plus sigma s d w, and the other model, which is the log normal model, which is the finite time model. If you look at this, I have tried to analyze or to arrive at the results in context of application of two different models to the same set of data. The data that I have used is the mu is equal to 15%, standard deviation is equal to 30%, the initial stock price, that is S naught, is equal to 1000, the projected stock price that we want is S t, let us call it S t is equal to 1054, and the time frame we have taken as 1 week, that is approximately 0.0192 years. If I use the infinitesimal model, work out the mean is mu into s, and the standard deviation is sigma s root dt, where dt is given by this. I get this z value is the corresponding standard normal variate of 1.2286. Now, if I do the same exercise using the log normal model, and then I have log of s is equal to this much, and mean of log of s is so much, standard deviation of log of s is given, and therefore, I work out the z value corresponding to the log normal distribution, and I find that the z value here turns out to be 1.21. So, there is definitely a difference between the two z values, which will translate to different probabilities. You see, what are we trying to do in this problem? We are trying to work out the probability of the stock price achieving a value of 1024 1 week from now, if the price today is 1000, and these are the given parameters, mu is equal to 15% and sigma is equal to 30%. This is given to us. Today's price is 1000. We want to work out the probability of the stock price reaching 1054 1 week from now. And we find that if we use the infinitesimal time model, we find the z value as 1.228. Of course, probability can then be easily read off from the normal distribution table. And in the case of the long term model, that is the log normal model, I arrive at the z value of 1.2154. So, there is a difference which will obviously translate to a difference in probabilities. This model will give you a slightly higher probability, this model will give you a relatively lower probability. Now, you increase the time period from 1 week to 1 year. The rest of the inputs are the same, except that the time period, in other words, what we want now is, we want the probability of the stock price going to 1054 in 1 year from now. Stock price going to 1 year, stock price going to price 1054 at the end of 1 year from now. Its today's price is 1000 rupees, the mu and sigma are given as 15% and 30% respectively. If I use again the infinitesimal model, I end up with a z value of 0.32, which again give minus 0.32, sorry, which will again give me a certain probability. And if I use the log normal model, I arrive at a price z value of minus 0.14. So, here the gap has widened substantially. So, this shows that the objective of presenting these two sets of information is that the infinitesimal model is only relevant, is only valid in very small periods of time. When we you see, the basic thing is the correct model is unquestionably this model, the log normal model. However, it is approximated by the infinitesimal model for small infinitesimal small time periods. Therefore, when we used it for the 1 week time period, we found that we got approximately the same result, although there was a difference, but it was approximately pretty close. Here the difference has widened up substantially, substantial enough to be of far more significance, and the results would be substantially diverging. Therefore, I emphasize that while working out probabilities or while working out other confidence intervals and so on, if the period involved is say substantial, say exceeding 1 week or more, it is definitely better to use the log normal model. Log normal model happens to be the correct model. Now, a brief touch on why this difference in returns takes place, why the two models gives us different results. The basic thing is, you see, let us look at a situation. Let us look at a situation where the stock price starts at 1000 at t equal to 0 and ends at 1000 at t equal to 1 year from now, whatever the time frame is, the t equal to 1. Let us take it as 1 year. Obviously, it is quite logical that the return is 0 over this entire period. Now, suppose we split this full period of 1 year into two parts of 6 months each, 0 to 6 months and then 6 months to 12 months, and we find that at the end of 6 months the stock price has jumped up to 1100 and then again it has come down to 1000. We work out the returns for the first 6 months and we work out the return for the second 6 months. What do we find? We find that the first 6 months, because it is a 6 month period, give me an annualized return of 20% and the second 6 months give me an annualized return of minus 18.2%, which if I now take the average of these two returns, now instead of taking the working out the return over this entire period, what I am now doing is I am working out the arithmetic average of the returns over these two periods. I find that it has a slight positive value. Now, I do the same exercise with the stock price. Instead of going up to 1100, the stock price driving down to 900 and then again recouping to 1000. Again I find that for the first 6 month period the return is minus 0.2, that is 20%, and for the second 6 month period it is 22%. Again, if I take the average, I end up with a positive figure. So, what do I find? I find that in both cases, if the stock price goes up or the stock price goes down, by virtue of splitting the period into more than one part over which the return is calculated and then taking the arithmetic average, I am ending up with a higher return. Actually, the correct return obviously is 0, but because of the splitting up and then taking the arithmetic average, I am arriving at a incorrect figure of these positive values for the return. That is why that correction, that mu minus 1 by 2 sigma square comes into play. This is an example of that. This is a description of what I have just explained. The return over A, you have got 3 points here, A, C and an intermediate point B. The return over period AC is given by the change in price over AC divided by SA, that can be written as the change in price AB plus the change in price BC over CA. And the return over the sum of the returns over AB and BC can be similarly written as DSAB upon SA, but here when I calculate the return over this period BC, I shall take the denominator as this price SB, the price at this point and not the price at this point. Therefore, so the second part of my summation return is going to be DSBC divided by SB, not SA, and this becomes DSAB upon SA. This is as it is. And what is SB? SB is SA plus the change in price over this period. So, SB is equal to SA plus DSAB. SB is equal to SA plus DSAB. So, simplifying, what do I get? On simplification, I get this expression. if this expression that is the sum of the two returns is to be greater than the average of these two returns is to be greater than this return, then we must have that R A B plus R A C is greater than R A C. If you simplify this whole expression, then the requirement is d S A B into d S B C must be less than 0. That means, there must be one up movement and the other should be down movement. The signs of d S A B, that means sign of the change in price over here and the sign of change in price over here must be in opposite direction. So, that is what happened in the previous case that I illustrated, and that is why we found that we end up with a certain positive return when we take the average return over 2 periods instead of taking the entire period as one period and then working out the return. That is basically because of this factor H B coming into play. Right. So much for the recap. Now, because we have been talking extensively of log normal distributions and the stock price follows log normal distribution, it is worthwhile to spend a few minutes to talk about the PDF of the log normal distribution. In any case, we shall be needing it if we do risk neutral pricing and in the context of Black-Scholes model as well, and to understand its mean and variance. So, if x is log normally distributed with probability of rho of x, PDF rho of x, probability density function rho of x, x is log normally distributed with probability density function rho of x, then let y equal to log x, then y is normally distributed. X is log normally distributed means log of x is normally distributed. I repeat, if x is log normally distributed, then log of x is normally distributed. So, log of x we are writing as y. So, y is normally distributed. Let the parameters of the distribution of y, not of x, let the parameters of the normal distribution of y, which is log of x, be lambda and theta square. Lambda is the mean and theta square is the variance. Then obviously, P y being the normal distribution, normal density function is 1 upon under root 2 pi theta square exponential y minus lambda square upon 2 theta square. This is the standard PDF of a normal distribution with a mean of lambda and a variance of theta square. Now, this is the important part. The probability that the random variable x, capital X, lies between two values x and x plus dx. Which variable? The log normal variable. The probability that the log normal variable capital X lies between x and x plus dx must be equal to rho of x into dx. This is the definition of probability density function. So, nothing more about it. Rho x into dx must be equal to what is now x is equal to y is equal to log of x, right. So, if x is to lie between small x and x plus dx, that means y is to lie between log of x, that is log of small x, and log of small x plus dx, because y is equal to log x, right, and log x is a monotonic function of x. Therefore, probability that x lies between an interval is also can be also represented in terms of the probability that log x lies between another interval, which is given by log x and log x plus dx. So, in other words, I repeat, probability x lies between x and x plus dx is equal to probability that log x lies between log x and log x plus dx, and this log x is nothing but y. So, writing log of small x as y, writing log of small x plus dx as y plus dy, this expression can be written as p of y less than capital Y. This is capital Y, please note this. We have already defined it here. A capital Y is equal to log of x, we have defined it there. So, this is equal to probability y is less than capital Y is less than y plus dy. In other words, capital Y lies between the values y and y plus dy, and that is given by what? That is given by the PDF of y, because we are talking about infinitesimal intervals. So, that is given by the PDF of y, which is this expression. Remember, y is normally distributed. So, that is given by the PDF of y into dy. Now, making this respective substitution, p of y is equal to p of log x, reverse substitutions, and dy is nothing but y plus dy minus y. So, it can be written as log of x plus dx minus log of x. So, log of p log of x here, and this expression log x plus dx minus log x, you can simplify by the standard Taylor expansion. You get log 1 plus dx plus x into log x minus this log x, that gives you log of 1 plus dx, which you expand to the first term, you get dx upon x. So, this whole term translates to p of log x into dx upon x. Log of 1 plus x is equal to x minus x square upon 2 plus x cube upon 3. We retain only the leading term, which is x, and here the first leading term is dx upon x. So, we truncate it at dx upon x. So, p of log x into dx upon x. Substituting the value of p of log x, p y is given by this, therefore, p log x will be given by this expression. This x comes here, this dx is this x is this x comes here, this dx comes here, and p of log x is obtained from here by substituting y equal to log x. And this dx now cancels with what? This dx now cancels with rho dx, this dx and this dx cancels, and we get rho x is equal to this expression without the dx. So, that is this expression. Instead of dx you have 1 upon x under root 2 pi theta square exponential log minus log x minus lambda whole square upon 2 theta square. This is the PDF of the log normal distribution, where lambda and theta are the mean and variance of log of x. Please note this point carefully. Lambda and theta are the mean and variance of log of x. Mean and variance is easy to compute. E of x is equal to x into f x. Simply computations here, we substitute the value of f x from the previous slide, 1 upon x, 1 upon under root 2 pi theta. Theta is outside the bracket, so theta square goes exponential log of x minus lambda upon 2 theta square dx. When you simplify this whole expression, you end up with now here there is one thing to be explained here. This expression is nothing but the normal distribution, shifted normal distribution with a mean of lambda plus theta square and a variance of theta square. So, this when you integrate it over minus infinity to infinity, this gives you 1. Therefore, this goes, and what you are left with is exponential lambda plus theta square upon 2. So, the mean of a log normal distribution where is given by exponential lambda plus theta square upon 2, where lambda and theta square are the parameters of log of x. And similarly, you can work out E of x square and you arrive at this expression, and using this expression you can obviously work out the variance also. So, this is the variance of a log normal distribution in terms of the parameters lambda and theta. Now, in our case, lambda is equal to log of s naught plus mu minus 1 by 2 sigma square t. We have talked about it earlier. This is the mean of our log normal distribution representing the stock price value at ST, and this is the standard deviation of the stock price value at time t in the log normal model. So, we have, on substituting lambda equal to this expression, theta equal to this expression in the earlier results, we get these two results. Mean of ST is equal to S0 exponential mu t, and variance of ST is equal to this expression. Right. Now, a few examples before we move towards the pricing of options. Consider a stock that pays no dividends, has a volatility of 30% per annum, that is sigma is equal to 30% per annum and provides an expected return of 15% per annum with continuous compounding. Has a current price of 1000, what is the probability of an increase of 54 or more in 1 week? Use the infinitesimally small model, assume that 1 week is equal to 0.192 years. This is the data that is given to us. Mu is equal to 15%, sigma is equal to 30%, S naught is equal to 1000 and the increase in price is 54. So, we want to work out the probability of the stock price reaching 1054 at the end of 1 week from now. The solution, volatility is given by this sigma and this is sigma, this is mu and this is S naught and this is T. So, in the infinitesimal model, the change in stock price ds is normally distributed with the mean of mu s dt. The mean is mu s dt, mean of ds, E of ds is equal to mu s dt and of course, sigma of ds is equal to sigma s under root dt. So, mean is mu s dt which is given as this and sigma s under root dt works out to be this figure. All the figures are there, sigma is 1000, s is 1000, dt is 0.012 and sigma is equal to 30%. So, everything is available with us and therefore, we get the mean and variance or mean or standard deviation of the stock price using the infinitesimal model as these two quantities. This is the mean and this is the standard deviation. Our desired price increase is this, therefore, we are looking at a price of 1054. So, 1054 is the price that we are looking at. The z value that we have is 1.2297 and the required probability is 1093. This can be found out from the normal distribution table. This value is obtained as the standard process x minus x bar or x minus mu divided by sigma, where mu is the mean. Mu in our case is 2.88 and the standard deviation here is 41.57. So, you have to use these figures, not this sigma, but this sigma 41.58. So, this would be the expected price increase minus 2.88 divided by 41.54, that will give you 1.22. Now, another problem. Now, we talk about the log normal distribution. The price of a stock follows the log normal distribution with mu equal to 17%, volatility of 20%, the current stock price is 100. What is the probability the price increases to more than 149 at the end of 2 years from now? Now, there we are talking about a time frame of 1 week, here we are talking about a time frame of 2 years. So, therefore, let us work it out. The expected return mu is 17%, volatility is 20%, current stock price is 100 and the projected stock price that we want to be exceeded is 149. The time horizon is 2 years. The expected value of log is given by log st is given by log s0 plus mu minus 1 by 2 sigma square t. We have done it just now a few minutes back. So, that works out to 4.9052 and the standard deviation of log st is sigma root t, which works out to this. Sigma and t are given here, mu is also given here and s0 is also given here. We can work out log of s0 and we can work out this mean. Now, then we work out log of 149, because remember these two mean and variances are mean and variances of log st. They are not mean and variances of st, they are mean and variances of log st. Therefore, we have to handle even the projected stock price also in terms of its logarithm. So, the log of 149 turns out to be this. In other words, we want to find the probability of log of st, that is the log value exceeding 5.0039, provided that it is normally distributed and it has a mean of this expression and it has a standard deviation of this expression. I repeat, we want to find out the value of a variable or the probability of the variable exceeding this expression, provided that variable follows a normal distribution with a mean of 4.90 and a standard deviation of 0.28. So, we work out the z value. The z value turns out to be 0.3492 and the corresponding probability works out to 0.3632. Then we have a problem on Brownian motion. In a Brownian motion, we have a standard Brownian motion with mu equal to 0, sigma equal to 1. What is the probability of the process being 1 unit away from its initial value? Remember, we are talking about 1 unit away from its initial value, means it could be 1 unit up or it could be 1 unit below the origin. What we want is that the particle executing Brownian motion should be 1 unit above the initial value or should be 1 unit below the initial value. Both the probabilities need to be considered after 25 units of time. The problem is relatively straightforward. Mu is 0, standard deviation is sigma root t. Sigma is given as 1 because it is standard Brownian motion. So, sigma is 1, t is equal to 25. So, standard deviation is 5, mu is 0, and we want to find out 1 minus, we want to find out the probability that the particle is either in this region or in this region. So, we want to find out 1 minus probability that p lies between minus 1 and plus 1, x lies between minus 1 and plus 1. We want that x should not lie between minus 1 and plus 1. Therefore, we want to find out 1 minus p minus 1 less than x less than plus 1. In terms of the standard normal variate, because we have a mean of 0 and a standard deviation of 5, we have this is equal to 1 minus p minus 0.2 less than z less than plus, and that when you work it out from this normal distribution tables, it comes out to 0.8414. Finally, we have a problem on the representing again finance problem. A company's cash position measured in millions of dollars follows a generalized Wiener process, the generalized Brownian motion. It has a drift of 0.5 per quarter and a variance rate of 4 per quarter. So, because it and we want to find out the initial cash position such that the probability of bankruptcy at the end of 1 year from now does not exceed 5%. I repeat, we have to find out the initial cash position such that the probability of bankruptcy at t equal to 1 year from now does not exceed 5%. We are given that the drift rate is 5 per quarter. Therefore, the mean or the expected value of the Wiener process that governs this cash position is given by 0.5 into 4 quarters. So, that is 0.5 into 4, that is 2, and the variance rate is 4 per quarter. So, the variance over the entire period of 1 year will be 16. Let the initial position be x, right. So, the final position will be normally distributed with a mean of x plus 4 into 0.5, that is what I mentioned just now, and a variance of 4 into 4, that is x plus 0.2 and a variance of 16. In other words, what we want is that the probability of bankruptcy should be 5% or less. See, this is the probability of bankruptcy. The mean is this expression, the variance is this. So, if you work out the standard normal variate, it is 0 minus x plus 2.0, this is the mean, and this whole expression divided by the standard deviation, which is 4. So, this expression, the z value should be the z should be less than this value in order that bankruptcy should be there. And we know that this probability of z being less than this is equal to 0.05 or lower. Now, from the normal distribution tables, the value of z corresponding to a probability of 0.05 or lower works out to minus 1.645. Therefore, we must have this this whole expression, this expression equal to minus 1.645, and that gives us x equal to 4.58. Let me repeat this for a minute quickly. This is my probability distribution for the stock or the cash position that turns out to be n. This is the mean, x plus 2, and this is the variance. Now, we want the cash balance or the stock balance to be 0. So, if you want the stock balance to be 0, what would be the corresponding z value? The corresponding z value will be equal to 0, that is the value that we want, minus the mean divided by the standard deviation. So, we want the cash balance to be 0 or negative. 0 or negative. So, that z must be less than 0 minus the mean, and that is what you think z, this is actually z should be less than this quantity, or z should be less than, but we are given that the probability of z being less than this quantity should be less than 5%. In other words, this expression, probability of this expression should be less than 5%. But from the normal distribution tables, we find that if the probability, if we want the probability to be less than 5%, then the z value has to be the cutoff z value is equal to minus 1.645. In other words, this expression must be equal to minus 1.645, and that is precisely what is done here. So, that we end up with x is equal to 4.58. We will continue after the break. Thank you.